Everyone, welcome to the UFS webinar. This webinar is hosted by NWS OSTI. The goal of this webinar is to enhance communication and share advancements in the aspects of UFS, both in research and operational settings. My name is Stacy and I work with Yan Zhu, who is the program manager at OSTI, and I'm here to help coordinate and deliver the webinar. And you can feel free to contact us if you have any comments or suggestions. First, I'd like to share a couple housekeeping items with you all. The webinar is in listen only mode due to the high number of attendees. And if you have any questions now or during the event, you can submit them via the question or chat tab on GoToWebinar toolbar. And excuse me, the toolbar is on the right side of your screen. Okay, and the presentations last for about 45 minutes, and the questions and answers will be for 15 minutes. Okay, so Daryl Kleist, you will be introducing the speaker, which is Amal Akkraoui.
Thanks, Daisy. So hi, everyone. My name is Daryl Kleist from Weather Service NCEP Environmental Modeling Center. It is my distinct pleasure to introduce our speaker today, Amal Akkraoui from NASA GMAO. She's a lead research scientist there, working on atmospheric DA for NWP and reanalysis applications as part of the Earth Science Division. She completed her PhD at McGill in 2010 and joined Goddard shortly thereafter, where she's done a bunch of research on things like the BiCG algorithm, the minimization algorithm, ensemble variational hybrid DA, background error estimation, and the use of stochastic physics for error representation. She's also collaborated with the OSSE group to examine error properties in the DA. Most recently and relevant to the presentation today, she's been focused on reanalysis work, which is particularly relevant to the UFS as we start thinking about our own reanalysis efforts leading up to GEOS version 13. So with that, I'll turn it over. Amal, we're looking forward to your webinar today. Thank you.
Thank you, Daryl. So I'll start full screen here. And just let me know if you see all of my screen.
Yes, we see your screen.
Okay, perfect. So thank you everyone for the invitation. In this talk, I want to present some recent developments in reanalysis at NASA GMAO. And specifically, I want to focus on this transitional plan that we have that would take us from MERRA 2 to MERRA 3 through a new atmospheric reanalysis, GEOS R21C. Like any reanalysis effort, this is serious teamwork, and I would be remiss if I did not acknowledge the contribution of a large number of people that cuts across many teams within GMAO. The list would be unfortunately too large to include in one slide, and so I'm listing here only the people that have contributed directly to the content of this particular talk, and I will be acknowledging the rest of the folks as we go along with the slides. So at GMAO, we continue this incremental progress towards an integrated Earth system reanalysis through a combination of systems with increased levels of complexity and coupling. And currently, we're working on a new 25+ atmospheric reanalysis product called GEOS R21C, and it stands for Reanalysis for the Early 21st Century. It is planned as a modern baseline for the atmospheric components of the future coupled reanalysis MERRA 3, and I'll explain the nuances between them in the next few slides. As part of the plans for R21C, we'll be producing also 2 offline derivative products, one for the chemistry and one for the cryosphere, and we are hoping that this will give us the opportunity to further understand the interactions between the atmosphere and other Earth system components. So in this talk, we'll be going through some plans and progress towards R21C and how it fits between MERRA 2 and MERRA 3. In this schematic, we have the GMAO reanalyses and their respective derivative products. As some of you, most of you know, GMAO already produced 2 atmospheric reanalyses, MERRA and MERRA 2. MERRA 2 is still ongoing now in near real time. And with each of these reanalyses, we have derivative products that aim to explore aspects of other components of the Earth system in the long time frame of reanalysis. So, for instance, in MERRA, after MERRA we had MERRA Ocean, MERRA Aero for the aerosols, MERRA Land, and MERRA Ocean Biochemistry. And for MERRA 2, we already had a MERRA 2 downscaled product to 12 kilometer. And currently in production, we have MERRA 2 Ocean, which is an ocean data simulation reanalysis that will feature a coupled model for the atmosphere and the ocean. We have also SCREAM, which is a stratospheric reanalysis for the chemistry with MLS. So all of these components in here, whether for the atmosphere or the other Earth system, we believe that will give us enough insights that will lead us towards this MERRA 3, the goal of getting to MERRA 3, which is planned so far as a coupled data simulation and model reanalysis. The coupling includes the data simulation side and the model side, and the coupling would include the atmosphere, the ocean, and ice, with some type of coupling for the chemistry and for the land. We believe, however, there is still some way to go before we can get to the system that will be that we will base MERRA 3 on. And in this talk, we will be talking specifically about this transitional period that will take us from MERRA 2 to MERRA 3. So in this slide, I just want to highlight why we think that we need something in between MERRA 2 and MERRA 3. So by looking at the timeline of all the progress that we had in our forward processing system, MERRA 2 sits really far away from MERRA 3. As a product, MERRA 2 is relatively new and is still serving the reanalysis and research community very well. But the system that MERRA 2 is based on is starting to feel a bit outdated. It's a 3D VAR system, 50 kilometer, for instance. And since then, we have upgraded our system significantly, both on the DI side and on the model side. And by the time we get to this JEDI-based coupled data simulation with all of these components of the atmosphere, the ocean, the land, and chemistry, and the coupling that will be in MERRA 3, the system that was used in MERRA 2, we fear that it will become completely irrelevant. And so I think that we are well positioned at this time to get something that is that bridges this gap between these two reanalyses, that will offer us more insight about an updated insight actually about the atmospheric components by being able to test all of the upgrades that we did since MERRA 2, and also considering all the byproducts that are currently either in production or will be accompanying GEOS R21C. For instance, the SCREAM will give us insight on the stratospheric chemistry, MERRA 2 Ocean on the ocean data simulation and the model coupling. The PolarMERRA downscaling byproducts of R21C will give us this focus on the cryospheric region, and the GEOS R21C Chem, an offline reanalysis product that will do a reanalysis of the chemistry, not only in the stratosphere, but also in the troposphere. So all of these components are updated, will give us updated information that all will lead to MERRA 3. And we believe that this transition will be better served by having these intermediary steps that will lead us towards the MERRA 3. So basically what GEOS R21C is, it's an enhanced atmospheric reanalysis that builds on the advances introduced both on the DA side and the model side in the GEOS forward processing system after MERRA 2. It's focused on the early 21st century, hence the name, because we want to still give this focus on the NASA observations, and we want to look at the NASA EOS to post-EOS observations. The configuration that will be used for R21C, is a 25 kilometer horizontal resolution, and this is higher than the resolution used in MERRA 2. It will also use a hybrid 40EN VAR and all-sky data simulation. As I said, we'll have two derivative products, one a reanalysis for atmospheric constituents that will be using the constituent data simulation system that is actively being developed now, and GEOS Chem as a chemistry model. and the other product is a PolarMERRA downscaling, which will be enabling us to focus on the cryospheric processes. What we're hoping also is that R21C would be a potential step towards a level 4 product for NASA's precipitation measurement mission science team. One important thing to understand about GEOS R21C, and if there is anything to take away from this talk, is this first bullet, is that R21C is not a replacement to MERRA-2. MERRA-2 was a replacement to MERRA. MERRA-3 is probably going to be a replacement for MERRA-2, but GEOS R21C stands on its own because it has a specific purpose. So it can be thought of rather as a stepping stone towards MERRA-3, providing a baseline for its atmospheric component and the opportunity to explore aspects of the Earth system coupling with other offline components. So for instance, for the atmosphere, we want to be able to evaluate all the upgrades that were introduced in the data assimilation system, like hybrid for the EMPAR and other DA updates. We want to look at ensembles because we've never had any ensembles in reanalysis. We want to revisit some features from MERRA-2 because, as I said, the product itself is new, but the system behind it, some features, may be revisited at this point. And also we want to look at the new schemes, the new physics schemes that were introduced in the forward processing system, which have a significant impact on the on our system, but we still want to see how they fare in a reanalysis mode. Through the 2 byproducts that we're planning to follow as a follow-up to R21C, we want to explore the links that will be essential in terms of coupling. So for GEOS R21C Chem, for instance, we understand that the coupling between chemistry and the atmosphere will depend to a large extent on the transport, the model transport. And so we want to spend some time to understand the drivers and impacts of changes in model transport characteristics so that we understand how that will affect also the chemistry and how we can use that information to do an online, possibly an online chemistry reanalysis when we get to MERRA-3. On the other hand, PolarMERRA downscaling is a collaboration between GMAO and the cryospheric lab at Goddard. And it is the opportunity to focus on the polar region, to look at cryospheric processes and the use of satellite data in those regions. Mostly when we do global reanalyses, we focus a lot on the global aspects of things. And if anything, this collaboration between these 2 teams will bring the 2 teams together to just zoom in on the polar regions and just say what's missing in terms of representations of some of these processes in global reanalyses. So this is in a nutshell what GEOS R21C is. And next, we'll be looking at some of the features that will be introduced. Maybe not novel features, but just some of the features that are essential to GEOS R21C. And we start with the observing system, the backbone of any reanalysis. And you can see by the list of the people that are contributing daily to the overhaul of the observing system for R21C, whether it be by processing the data, testing the data, and all sorts of testing and applications that are being done to ensure that the observing system is ready. The list is long and it's bound to get longer. The observing system in any reanalysis is an essential part because it's one of the main reasons why we consider sometimes updating a reanalysis product. When we update a reanalysis product, we usually get the opportunity to use reprocessed versions of older operational observations. So in R21C, for instance, we'll be using updated versions of MSWAY, AVHRR, AMVs, etc. It's also the opportunity to use new data. So we'll be using the ONS nadir profiler, the ONS nadir mapper, Cosmic 2, etc., which were not available for MERRA-2. And maybe most importantly also is the opportunity to improve the use of observations. MERRA-2 used an all-sky framework, and R21C will be using new and old observations in all-sky, in the all-sky framework, and this is great. Another aspect related to the observing system for reanalysis, which sometimes we forget about, and that is that reanalysis systems are frozen. And so the ability of older systems to ingest new types of observations is very limited. With instrument failures, they start running out of data. What we usually like when looking at a plot like the one here on the left that shows the observing system of MERRA-2 throughout the years, we're really happy that in the recent years we're using all this great observing system, modern, and all of these satellites, etc. But we have to understand that things are frozen here. Anything that breaks is not replaceable, and anything that's new, MERRA-2 would not be able to ingest. So for any reanalysis, and this is not only for MERRA-2, but for any reanalysis, it should not run past its prime. It should not get to that point where it starts losing data or running out of data, because the constraint the data applies, on the analysis is very essential, especially in a reanalysis context. We were able to illustrate this by a little study that we did last year that looked at the parallel streams of MERRA-2 and how different they are when we're using better or like a good observing system or not so good. The difference between parallel streams that are assimilating exactly the same data is larger when you don't have enough of these data, like here in 1991, as opposed to 2010, for instance, where two streams running in parallel assimilating the same data will give you similar solutions. So that gives us more confidence that the analysis that we're producing, is constrained enough by the data to have that kind of confidence. And a reanalysis that goes beyond that point where it starts losing data, it's almost like it starts going back in time and producing an analysis or analysis fields where we don't have really enough confidence to say that these are good, because if you run the system twice, you might get a different answer. You don't have enough constraint from the little data that you're still left with. So gladly, MERRA-2 is still not at this point yet, and not for a few years, but this is just a general aspect about reanalyses and the observing system that we need to always keep in mind. Okay, next let's talk about ozone in GEOS R21C. And ozone is receiving special attention for this reanalysis because we have a special goal that is set beforehand. We want to minimize as much as possible the artificial discontinuities in the ozone record that usually arises from the observing system changes. And we want to avoid that by applying some homogenization of the input product. And when that's not possible, we want to at least be able to quantify expected remaining discontinuities. So unlike MERRA-2 that used only SBUV, OMI, and MLS, GEOS R21C will use more data and different types of data for ozone. So it will use updated versions of SBUV, OMI, and MLS, but it will also introduce the limb profilers and the nadir mapper. For the first time, we'll also be assimilating ozone-sensitive radiances from AIRS, IAZI, and CRIS. And all of these novelties will introduce sources of discontinuities. So relative biases among data sources in a changing observing system can lead to discontinuities and pose a problem for trend studies. And we want this for R21C, we want to test this idea that we want to get an ozone record that may be fit for trend studies. In MERRA-2, we had to deal with the SBUV to AURA transition in 2004, and that was a major disruption in the time series of ozone. In R21C, we might still have to deal with that, but at least for the introduction of the limb profiler and the nadir mapper, we want to be able to do some homogenization that will ensure continuity in total column ozone and the ozone profiles. And I'll show this in the next two slides. So the plot on the left here is showing a time series of MLS data, and then in black here, and then in this golden color is showing the limb profiler without any adjustments. So if we don't do anything, we see that the time series of MLS has a different mean compared to the limb profiler. And so we're bound to have some type of discontinuity in 2012 when we introduce the limb data. The adjustment that is done right now is eliminating discontinuity by a latitude, pressure, and month-dependent adjustment to the limb profiler data. And so GEOS R21C will assimilate the adjusted data rather than the original one. The discontinuity would be limited in here because now both systems are homogenized, and we're leaving it to the data assimilation to address any of the changes in the information we're getting from these two types of ozone measurements. The same thing we are doing for OMI and the nadir mapper, where on the left we can see that the climatology of the difference between OMI and the nadir mapper shows systematic differences that are seasonal. The plot here is showing the climatology by month, but also latitudinally dependent. And when we remove the relative bias between them, so we remove it from the OMI data, we get an adjusted product that is consistent with the nadir mapper and at least gives us, avoids this discontinuity that we might see in the total column ozone. So GEOS R21C will assimilate adjusted OMI data. The last slide about ozone data is about the radiances, or the ozone sensitive radiances. So the assimilation of sensitive channels, ozone sensitive channels at 9.6 micron has been shown to significantly reduce the departures from observations. We're using here AIRS, IASI, and CRIS, and this is illustrated on the left by looking at the departures from OMI on the left-hand side, with and without the radiances, with the assimilation of the radiances in the bottom, and without these radiances are on the top. So the departures are significantly reduced, and the same thing on the right-hand side for the comparison with the nadir mapper. Okay, moving on. Another feature for R21C that is relevant to the observing system is the use of all-sky framework. And the goal here is to assimilate SSMI, TMI, EMSR-E, EMSR-2, GMI, MHS, and ATMS in all-sky conditions. The framework has already been implemented in GEOS-FP for some time, and now currently we have GMI, EMSR-2, and MHS that are operational, and in all-sky, I mean. And soon we will have also ATMS that is added, and all have been shown to have a positive impact. So for us, from a reanalysis perspective, all we have to deal with is the introduction of SSMI in all-sky, TMI, and EMSR-E, all the instruments that are not available in near real time. So the impact of assimilating GMI and EMSR-2 in all-sky radiances have been shown to be positive, and this is shown here on the left-hand side by looking at the impacts for observations. That is showing that EMSR-2 and GMI have the largest impact per observations. That impact doesn't really translate in the total, not so much in the total impact, just because we don't have enough of these data to make it to the top of the list. But per observations, they have the largest impact, and that is what's meaningful. And we expect also the historical data for R21C to have a similar impact. And so this is the timeline for the observations that will be used in an all-sky framework for R21C. MERRA-2 only used rain rates for TMI, and now it will be used entirely as in an all-sky framework. And then GMI, EMSR-E, and EMSR-2. SSMI and MHS were used in MERRA-2, but only in clear sky, and now they will be used in all-sky conditions, and then we'll be adding as ATMS as well. Okay, now we'll move away from the observations, and we'll start looking at some other features related to other aspects of the reanalysis. And we'll start with this, with the re-examination of a feature that was in MERRA-2, and now we're starting to question whether we can use it as is, or to try some type of modification to avoid an issue that was discovered recently. And this is related to a constraint that is applied on the analysis increments in order to conserve the dry mass. So technically, the globally integrated tendency of water or water storage should be governed by the difference between surface evaporation and precipitation. And that has not been the case in previous reanalyses like MERRA and ERA interim, for instance. That black line that is shown on the plots here for the water storage is not consistent with the blue lines that are showing the evaporation minus precipitation. And as a result of that, the precipitation actually had spurious jumps that were mimicking or that were responding to the changes in the analysis increment due to changes in the observing system. So this property actually of this discrepancy between the water storage and the E-P was not really that desirable. And so in MERRA-2, a constraint was imposed on the analysis increment so that globally, in a global integral, it would vanishes and it would allow only the E-P to govern the water storage. And it worked beautifully really as designed, because when applied in MERRA-2, it did what it was supposed to do, which is conserve dry mass, and it provided the E-P balance that we wanted. It also reduced those spurious jumps in precipitation that were due to the observing system changes, and those jumps, we understand that they were artificial. Now, the problem that we're finding right now was that while this sensitivity to the change of the observing system was eliminated from the precipitation record, it seems to have been actually implicitly embedded in the adjustment that is happening at to the analysis increment. And this is seen here by looking at a time series of the analysis increment from MERRA-2 for specific humidity. On top, we have a time series of the increments after the adjustments, after the constraint is applied, and in the middle, we have the unconstrained analysis increment. And we see that for the most part, the features are almost the same. So there isn't really a lot of change, but in some areas and in some periods, we see especially, and I don't know if you see my mouse here, but especially here after 2010, below 900, the increment is reversing sign. So while the data are saying, for instance, dry this area, what the model is seeing or using is the adjusted increment that is saying, well, now we need some moisture. And this, from a DA perspective, is really hard to accept. By looking at the the lower panel that shows actually the work of the constraint or the constraint adjustment, we see that the constraint is starting to play a much bigger role than originally thought, and a much bigger role after some significant changes to the observing system after around 2009 or so. So we want to address some of this before we start R21C, and so we're playing around with the formulation of the dry mass constraint. And in the title here, I'm putting attempts because these are so far still just attempts. We're looking at a reformulation that hopefully will still achieve the same goal, which is to conserve the dry mass, but with minimal impact on the analysis increment. So what I'm showing here is just an example of some of the formulations that we were testing. On the top panels, I have the analysis increments, a cross-section of the analysis increment of specific humidity for the control on the left, and one of the variations on the middle, and then the latest one that we're trying on the right. And on the bottom, I'm just showing the effect that is due to the constraint. By changing the formulation, we can either make the constraint act only in areas where the increment is present, and that this is what we're calling, you know, the no data, no harm. But this variation here in the middle seems to backfire a little bit. And then the most recent one that we're still testing at the moment is a variation that is focusing really just on the dry mass constraint, and it seems to have very minimal impact on the increments, as seen here by you know, we're dividing with the constraint effect, you know, by 10 in order to get the same colors. So it's really it's having a very small impact on the increments. The jury is still out on this one, however, because the testing just started, and we need to validate this more thoroughly. Depending on the compilation of all of these tests that we're doing for the constraints, we'll be proposing, you know, recommendations for R21C, and we'll take it from there. Okay, so I'll skip these three just to go to the next part. And in this part, I just want to go back to what I said before, that we understand that R21C has a special has a special mission, and with the byproducts that are associated with it, we want to take this opportunity to explore some aspects of the coupling that we may not have time to, when we get everything together for MERRA 3. So this is the time to do it while we still have, enough time. So the one question that we've been really keen on trying to explore as much as we can is the model transport, because it affects the chemistry directly. So the objective of this little work was to evaluate the dynamical, convective, diffusive transport characteristics of the candidate systems for GEOS R21C, because the transport evaluation is relevant directly to the constituents, and that will be the major part in the reanalysis, the offline reanalysis product for chemistry. There are many ways we can explore the transport characteristics. We can focus on the tropospheric transport in terms of looking at the short range tropospheric transport of constituents, or we can focus on the stratospheric part, where the long range, long time scale transport involving the stratospheric circulation is of relevance. So for instance, we can look at the time scale of cross hemispheric transport. We can look at questions about the mean age of air, for instance, etc. And then the link between the two time scales, such as the upper tropospheric upwelling. There's a lot of work that goes into this, and unfortunately in a talk like that, it will be impossible to give it justice. But I just want to give one of the conclusions that where we are right now, after focusing simply, I'm going back here, we've been focusing mostly on the stratospheric circulation and stratospheric transport. And where we are right now and what we know is that this Brewer-Dobson circulation, the global mass circulation of tropospheric air through the stratosphere, has been getting stronger in more recent versions of our GEOS model since MERRA 2. There were many indications that the MERRA 2 system was very comparable to what the observations that are usually used for validating things like the age of air, etc. And it seems that with multiple versions, multiple upgrades that came out of MERRA 2, the age of air is starting to get younger, and that would affect the transport or the chemical transports later on. So a faster Brewer-Dobson circulation appears to be related to changes in wave conversions in the lower stratosphere associated with changes in the zonal mean critical lines. We're exploring these ideas actually a bit more in detail because we want to get to drawing a clear link between clear causality link between what drives what to change that circulation. One point that is of direct relevance to the offline chemistry reanalysis that we're planning is two questions that are essential. The first one is, this product is going to be an offline reanalysis, so it's going to take the atmosphere from R21C. It's going to be driven by R21C atmosphere. So we were asking the question whether using an offline procedure, like what we're calling here a replay, does it do a good job in reproducing the characteristics of the transport as if we were cycling the data assimilation system as in the reanalysis? And the answer to that one seemed to have been yes, the replay does a good job. So we're okay with just doing a replay of the chemistry. However, the bad part of that answer is that the fidelity of the transport in replay simulations ultimately rests on the fidelity of the data assimilation of the DAS, in R21C. And that means that the atmosphere of R21C has to have a good transport for the chemistry in the chemical reanalysis to have a good transport as well. We're thinking of this question of model transport as a long-term project that hopefully will go beyond, just what we're doing for R21C. By getting the reanalysis, the chemistry reanalysis, we will start looking at questions of the direct impact between, those transport characteristics and the actual chemistry, and maybe probably all of that will lead towards some developments and recommendations that we want to address before we start MERRA 3. The other byproduct is the PolarMERRA downscaling, and as I said, this will be the opportunity to focus on cryospheric processes. So this is the collaboration between GMAO and the cryospheric lab, and it has been a great collaboration so far. And like the chemistry, we see it as a long project that probably will go beyond R21C and beyond also the PolarMERRA downscaling, because we want all of that to feed into MERRA 3. One thing that was interesting to collaborate with people whose sole focus is on the polar regions is that we're getting insight on some of the low-hanging fruits that we can maybe just implement with small tests and without much trouble, that we can change and add to R21C to make it better. And one of these suggestions was related to skin temperature over sea ice. So over sea ice, the model skin temperature is a product of the surface energy budget. And part of the surface energy budget is this ocean heat flux that is conducted through sea ice. In the absence of proper coupling between the ocean, the ice, and the atmosphere, all we have is a parameterization for the parameterization, to represent that. And that parameterization is the Newtonian relaxation of skin temperature to 0 degrees on a tunable time scale. So apparently that time scale has been set for like a long time ago, pre-MERRA 2, and probably even way before that, but it has not been revisited since. And the proposition here is that, well, it's easy to just test because it's just a simple parameter that we can play with and see the sensitivity of the system to that change and what it can do. And so this is what we did. We did a few experiments where we changed the Newtonian relaxation time scale from the 24-hour that is set for right now to 2 days and 5 days. And what we're looking at in here is just the agreement with AIR's data compared to the analysis, the skin temperature in the analysis. And it shows that the current 24 hours, it gives us, warmer temperatures compared to AIR's. The 2 days seems to be in better agreement, and then the 5 days we're overshooting to the other side, and things get really cooler. There is still a lot to do in terms of an evaluation of the impact of such a change, not only on the skin temperature, but on other things, like the upper layers, and maybe who knows, some other impact, on outside of the polar regions, for it to be a viable option, to recommend and use for R21C. But if this happens, this would be a very nice contribution from this collaboration that we have with the PolarMERRA team. Okay, so lastly, I just want to show just one slide of some encouraging results from prototype R21C. So as we integrate the system together, we are doing some of these tests just to see, how the testing of some new observing system with OSKY or all of these aspects of R21C, how they are applied, and the impact of each one of these. And we're doing some of these with a prototype that is not using the most recent version of our system, but close enough. So in here, what I'm showing is the root mean square difference with ERA 5 for specific humidity. And I'm showing first MERRA 2. On the left, this is the zonal mean of the difference, the total RMS difference between MERRA 2 and ERA 5. And then we could decompose that in terms that are relevant to the bias. It shows, how the differences in the biases are, differences in the amplitude, and differences in the phase. And what this is basically saying is that we have a large difference between MERRA 2 and ERA 5, and that difference, most of it is in the phase. We have also non-negligible difference in the bias. One of our prototype tests that we did for the period of 2015 is showing that, well, now we're having a reduced difference with ERA 5, both in the phase and in the bias. And this is just saying that this prototype is getting closer to a more recent reanalysis like ERA 5 than MERRA 2 is, and this is technically a good thing. Of course, we're not going to limit our validation of any prototype for R21C only on comparisons with ERA 5 or any other reanalysis. We'll be looking at a complete set of validations before we are happy with what will go on in R21C. So here is the tentative production plan. So as I said, the result that I just showed was using an older version of our system, and this summer and this fall we are hoping to produce an updated prototype with the most recent system that's technically the candidate system for R21C, and this hopefully will integrate all the components that have been tested so far separately. If everything is validated to satisfaction, then hopefully we can start the parallel streams for R21C. The GEOS R21C Chem will have to wait until the parallel streams reach the near real time, and for about a year or so. And that time is enough, actually, is a much needed time also for the constituent data assimilation system to continue some part of the developments that are needed for GEOS Chem. So the time frame works out perfectly. PolarMERRA downscaling, there's a TBD about the start date, simply because there is a lot of model developments that are desirable to be included in the model that will be used for the downscaling. And there's also a desire maybe to use a variable mesh that will extend outwards of the poles, and that will allow more focus even on the polar regions. The only thing is that we still don't know if that is a viable option or not. But at least the model developments that are planned for PolarMERRA, all of them actually are relevant and important, and they would also have relevance when we think about MERRA 3. Okay, so this is my last slide of the summary. This is just reiterating everything everything I presented before, that GMAO is preparing to produce this new 25+ year atmospheric reanalysis for the 21st century. It's planned as a stepping stone towards the decadal goal of producing MERRA 3 as an integrated Earth system reanalysis with multiple aspects of the coupling. And preliminary tests from some of the prototypes R21C are encouraging, and we're looking forward to getting to that point where actually we're looking at actual results from the production streams. And there is still a lot of ongoing work. I'm not going to list all of that. This is just, there's a lot of work that goes in, and hopefully we'll get that soon to be part of the prototype and the production. It has been really a pleasure and a privilege for me to work on reanalysis. This is the first time I work on any reanalysis aspects, and I really look forward to maybe a follow-up, or just looking forward to the next time when we get to present R21C as a product, and we see how it's leading us towards MERRA 3. Thank you, and I'll take any questions.
Thank you, Amal. That was very interesting. I want to just reiterate, if anyone has any questions, please type them in the questions or the chat box, and we will read them. Okay. Do you see questions, Amal?
Okay, so I'm just going to stop sharing, and then I'll go to questions.
Mm-hmm.
I can't see the questions, unfortunately. I don't see anything. So if anybody can just read the questions and I'll answer.
Yes, I will do that. Just one moment. Okay, we have a question here that says, nice talk. Are you planning to use the 4D NVAR solver for coupled DA?
The coupled DA aspects and what we'll include in terms of, is it a 4D ENVAR, is it a 4D VAR, is it a hybrid, etc. Those are questions are still for later. But for R21C, at least, we are going to use a hybrid 4D ENVAR for the data estimation side.
Okay. So far, that is the only question. If anyone has any questions, please type them. So far, Amal, that's the only one.
That's okay.
Yes, I guess you explained everything very well. Thank you very much for that.
My
So
pleasure.
this webinar has been recorded and it will be posted on our YouTube page. And if you all have any questions, you could please type them in the chat box, or you can also send an email of any questions you have. I will forward them to Amal. And
Perfect. I would be happy to respond by email as well.
okay, great. Thank you all very much. And thank you, Amal. That was very interesting. Hope to
Thank you.
hear from you again.
Thank you for the invite.
Absolutely. Okay, bye, everyone.
Bye-bye.